Hi, I'm Kyle, and this is Moose, and today we're going to talk about meniscus effects on a tilted plane. There's a couple things we have to go over, topics from surface phenomena before we can really talk about meniscus effects on a tilted plane. The first of which is the nature of how a surface is wedded when it comes in contact with water. And we can describe that in one of two ways. The first is hydrophilic, and hydrophilic means that the surface is more attracted to the water, and you'll see a better nature of how the surface or the water interacts with the surface. You will see it forms this type of droplet look. And the other is hydrophobic, and this is where you see more of a bead of water. You also see that it comes up and around and back down. What you'll also notice is that I've highlighted some angles on either one of these droplets. For the case on hydrophilic, this contact angle is less than 90 degrees. On the hydrophobic, it's greater than 90 degrees. And that's how we can describe our surfaces, whether they are hydrophilic or hydrophobic, based on how they interact with water and how they are wedded. So we have to talk about a couple other things, one of which is Laplace's equation. Now, Laplace's equation talks about the differential pressure created in an interface between a fluid and a vapor based on the surface tension of that interface and the curvature of the interface. What's important to note is that there is a differential pressure at the interface. And now we're going to talk about what that means. So everybody has seen a small beaker in a lab, and when they pour water in it, it creates this meniscus look. Now that meniscus has a contact angle with the glass of the beaker, which you can see I've highlighted here. It also has this form here. And this form is caused because there's a differential pressure between the air in the beaker and the air in the water. Now, differential pressure suggests that there's a vacuum pulling the water or the interface towards the water. This contact angle is less than 90 degrees, which would also suggest that glass is a hydrophilic material. Now, in our case, we're going to be looking at a plate or plane, in this case of glass. We're going to see something very similar. We're going to see that same contact angle as you see in the beaker. You'll see a higher pressure in the air and a suggested lower pressure in the water, causing this curve, which would again suggest a vacuum. Now, the height of this water meniscus against the plane can be calculated and derived from Laplace's equation to be 2 times the capillary length times sine of the tangential angle divided by 2. Now here, the tangential angle, for this equation rather, we look at the three-phase point, which is where the liquid, the solid, and the vapor meet, which is right here. And at this point, this tangential angle, phi, is just equal to 90 minus the contact angle. Makes it very simple for our calculations. Now, if you look at the diagram and the equations we're going to be using today for this experiment, you'll notice a couple things. You'll see the plane is tilted at an angle of beta. You'll see it has two heights, indicating the height of each meniscus on either side of the plane, being HL and HR. You'll also see that it indicates angles for the tangential angle for each. And you also see that the contact angle is the same on either side of the plane. That's because the contact angle is a characteristic of the material, and that doesn't change through the time of the experiment. The important thing to note here is that these equations can be simplified by taking a ratio of the heights, and that's what we're going to be doing today. We're going to be studying how these meniscus change, or menisci change, on a tilted plane based on the ratio of the heights on either side of that plane. So, if you'll take a look with me today, we're going to show you how I did my experiment. Move you over here slightly, and what you're going to see is a container. And this container is full of water, which I have dyed green with food coloring. Some other materials you're going to need today are a protractor to measure the angle of the glass that you're going to be putting into the water, some clean, pure glass. This time I got this as replacement glass for a picture frame. And what you're going to do is you're going to place the glass into the water. If you look very closely, you can see the water's moving a little bit, but you can see the meniscus forming on either side of the glass. And all you got to do is tilt the glass. You put it at the angle necessary, and again, you can see here, you can see the meniscus a little bit more defined on this side of the glass than you can on the other. And I'll show through the pictures that you're about to see that as you tilt it, that effect's going to change on either side of the glass. And you're going to see a higher meniscus on one side than you are the other, which is going to be related to our ratio. Now let me show you some pictures from my actual experiment. If you look at these, I'm going to show you two different pictures. One of which is with the glass tilted at 70 degrees. And here you can see that I've calculated the theoretical heights, or rather height ratios, based on a contact angle of the glass of 0 or 5 degrees. You also see that I have the experimental ratio underneath for comparison. And here we look again at 35 degrees. And at 35 degrees, you'll also see that the theoretical height ratio is pretty close to the experimental. Now, we're going to see slight differences because of hysteresis or effects of the material, purity of the material is coated, purity of the water. Here I've used distilled water and I've used as pure and uncoated glass as I could find. And I think the experimental results came pretty close. I hope that you found this video interesting and you've learned some new information.